Welcome back everyone, and this is a 3D printed actuator. Today I'll be showing you what it does, where I got it from, and some of the pieces I modified. 80% of these parts will be 3D printed, with the rest being a combination of gears, nuts, bolts, and washers. I'll also be showing you these cool stainless steel printed gears sent to me by PCBway, who is also sponsoring this video, but more on that later. A robot actuator is a mechanism that can turn energy into physical motion, giving a robot the ability to move. This is my first full robot build I've been working on for a few years now, and a couple of the same actuators, only larger, are used on each shoulder, where I'll be mounting arms for this robot in the near future. We're going to be putting together the exact actuator, only the smaller version of it, so let's get into that first. I did a Google search to find a free actuator for a robot. I typed in robot actuator thingiverse STL and I went to images 2 rows down, and I've already found the one we'll be building today. This actuator is on Thingiverse for free, and I'll leave the user account in the description of this video. Let's take a look at this open robot actuator. Luckily this user has listed all the parts, 3D printable and non-3D printable mechanical parts. They've also listed the amount of torque this actuator can put out using a NEMA 17 stepper motor. We're going to use most of the parts that are listed here. So let's go ahead and download all these parts, and I'm going to show you some examples of what actuators do and how they're used with robots. First, let's start with our pneumatic actuator, which uses compressed air to push a piston with a certain amount of force out of a valve. Once the piston has reached its limit, the air is released from a small air release valve on the actuator, and the spring returns the piston to its original position. Next, a hydraulic actuator uses a pump to push fluid through cylinders and move a piston in a similar fashion to the pneumatic actuator. Hydraulic actuators can use different hydraulic fluids, from petroleum-based, water-based, and synthetic hydraulic fluid. The last one we're going to look at is an electric actuator, and it's in fact the one we're using today. A 12-volt stepper motor will drive 4 spur gears against one another. The rotational force within the meshing gear teeth will multiply the torque from the motor to create a good amount of strength to move our lever and what may be attached to it. Besides these 3 actuators I've shown you, there's many different types and are used for a variety of tasks. Robot arms on car assembly lines like this typically use hydraulic actuators because they can generate an extreme amount of force and power, making them ideal in the industrial industry, like moving and lifting heavy parts, with the only downside being hydraulic actuators are more complex, meaning they need constant maintenance. For a full humanoid robot like some of Boston Dynamics' amazing models, hydraulic and electric actuators are used. Electric actuators are known for being very compact, flexible, and efficient, making them perfect for autonomous jobs. And Tesla's humanoid robot is quite impressive. I would even say is on par with some of the Boston Dynamics models. But Tesla's been pretty open about the type of actuators, and actually have shown the hydraulic and electric actuators that they use in their robots. They have a full video on their YouTube of the development of these actuators. There's more expensive as well as more powerful actuators for different robots depending on the design, weight, and budget for overall parts. Obviously today we're working with the 3D printed one, but nonetheless strong. So next we'll be assembling our actuator. Here's all the parts we'll be working with today. So as I said, I've modified a couple of the parts, and we're going to start with the first one, which is the actuator body. This body is what's going to hold all of our parts together, and we're going to start by putting our M4 rivets in the front and back of this so the screw can pull tightly together, clamping everything in place. Next, we're going to grab our main shaft and repeat the same process, only with 4 rivets on the front and 4 on the remaining opposite holes on the back. We're now ready to attach our NEMA 17 motor, but first we have to put this M3 35mm bolt through the hole by the motor mount holes, which will hold one of our gears. Then we'll mount the motor with 2 M3 6mm screws to the body. Here's the 3D printed gears we need, but instead of these cheap PETG plastic gears, we're going to be using our stainless steel gears that PCBway sent me. Having these gears made out of stainless steel is a big game changer. They'll be much more durable and long lasting for the friction and force that the teeth will endure over time. From small to big, we have our NEMA 17 shaft gear, 3212 gear, our 4012 gear, and our main gear. So now we'll take our main gear, which is the biggest gear, and snap it into place on our main shaft. Then we'll screw in 4 of our M4 20mm screws to the rivets we've attached on the shaft earlier. Next, I'll push our smaller bearing into place in the main hole in the middle of our actuator body. Once that's done, I'll push our larger bearing into our actuator cover. After, we'll insert the back end of our main shaft through the bearing. Once everything is in place, we're going to insert our 2 small bearings into the main hole on top of our actuator cover and one in the middle of the 2 holes right near the first bearing. This will be followed by inserting another M3 6mm screw through the bearing we just inserted. Now I'll start pushing the gears into place as well as the 2 of each of our M3 screws. I'll also place a couple of small washers in between my gears to reduce the friction from the constant movement of the gears against the plastic. Once all the gears are sitting where they need to be, I'll now attempt to close this together so I can screw the final screws into the actuator cover. It took a good second to get everything lined up without parts moving before I was able to close the overall structure. Once everything was closed and in place, it was time to put the NEMA 17 shaft gear on the motor shaft. I then used a couple of our M4 by 35mm screws to secure our actuator cover in place. After, I secured the protruding M3 bolts with M3 lock washers. The next modified piece is the cover for the NEMA shaft gear, and I'll screw this down with M3 6mm screws, also fully securing our NEMA 17 motor to our actuator body. Once this is done, I'm going to attach our 3D printed lever with a couple of M4 by 25mm screws. I'll definitely be inserting more screws to make sure everything is held firmly, but we're finished assembling our actuator. Now that everything is secured, I plugged in our motor and tested the actuator to make sure everything is working. All the gears are running smooth and the lever is turning with ease, so we're ready to move on to where I'm attaching this actuator. If you follow my YouTube channel, you may have seen I 3D printed a big robot head, and it moves back and forth, the eyes can blink as well as look left and right, and the eyebrows can move up and down. One thing I haven't yet finished is adding strong enough motors to be able to consistently move the head up and down and tilt side to side. Currently, I have these 2 servo motors that I built custom servo horns for that are holding the beams that support the front end weight of the head. But now I'll be removing these and replacing them with an actuator on each side. After removing the old servo motor holder, I screwed down both actuators on the right and on the left into the wooden panel disc on the base of my robot. Each actuator is separated by 2.5 inches in between them, lining up directly below where the holes on the rods attached to the robot head. We'll also be securing our metal rods to our levers with our M4 by 35mm bolts. Once that was done, I screwed in more screws to secure both levers so I can test the actuators. After they're firmly secured, I tested the movement of the motors as well as the lifting capabilities. Although the levers can easily lift each side of the head, I feel like at the base where each rod connects to the lever, it may break over time with the amount of stress imposed on it. I ultimately ended up redesigning and replacing our actuator cover to more securely hold back our bearing in place. The weight from the overall structure was also pulling on our main shaft. Once that was done, I reclosed both of my actuators. After securing this part, the bearing is held in place much more firmly. And last, I designed this circle disc to replace each lever that will rotate and move the bot head higher and lower as the disc completes a full rotation. This should give me the desired movement I want as well as more strength with each rod being closer to its actual axis. As you can see, the range of movement has improved on the robot, with it now able to lean left and right as well as set up a little higher than the original stance. As of now, what you're seeing is the first full code that I've written that runs on a loop on 2 different Arduino Unos, which makes everything work in sync. Now all that's left to do is write and upload different codes. This will make the movement cycles more smooth and the transitions much more organic, which for me is always the ultimate goal of me taking on any of these animatronic or robot builds. And thank you PCBway for sending me the gears that will keep this robot going for a good long time. Please everyone check out their site if you're interested. PCBway is a manufacturer and they specialize in custom PCB prototyping, production, 3D printing, PCB assembly, and much more. It's really the perfect stop if you're into any DIY or custom build projects. So that's going to be it for this video. I'll keep you guys updated or do a follow-up later down the line. But thanks everyone, and I'll see you in the next video. Please like, share, and subscribe. And if you have any question or comments, please feel free to leave them below.